Hello, everyone. It's really my great honor to present this work. What is the biggest trend in the next 20 years? Arguably, to me, I think this is we will become agent society, and the life expectancy will keep increasing. If you see, it used to be very flat until the Industrial Revolution, and then almost linearly rise in the last 100 years. So with this expectation, I think within 20 years, half of the population will need assistance. Are we ready? So I always ask myself, like 50 years later, should I expect my grandson to take care of me, my wife, their parents, their parents-in-law, their grandparents-in-law, or should I start work right now to really make robots or make some robots to take care of myself 50 years later? So if that is what I want to be a respected person, you don't use these old senior people 50 years later. So I need to, there are certain needs I will need at that time. So first, I need to, basically, a smart city, I need to go from A to B. Also, I need some robot that take care of myself, at home. And also, I need some very affordable healthcare providers, such that if I got disease, I won't go bankrupt. So once these services are massively deployed, I think the cost of service will go down. However, how we can go through this transition? From now, you only have 1 unit to 10 million units. So I think we really need trustworthy in this transition. And that arguably is the major obstacle right now for the intelligent robots. Trustworthy intelligent autonomy is not easy task. The main reason is, first, it has very high dimensional of design space, and also has a very vast of design, diverse tasks. We have very different sensors, and also we have different morphology of robots. Almost every kind of robot is totally different. And also we have very different environment to use them, and the way to define the tasks. So those models can be super big. It could be like a 0 gigabyte of parameters or even more. But however, to collect the data in the real world is really costly, and sometimes it can even be risky. So this mismatch between the demand in the input space and design space and our capability to safely collect the data is really the major challenge for trustworthy intelligent autonomy. So we need to be used to we need to be used to work in an area that data insufficiency is almost the default setting. So specifically, the challenge comes from twofold. One is the data will be collected in sequence. So you always have the safety in the long tail as a rare event. And also, the needs or tasks or scenarios also will unveil in sequence. So we will discover new needs and new situations gradually. So we need to be able to generalize in this case. So this talk is about how to really solve these two problems. And so first challenge, how we can solve the safety with extreme values. Because we always have extreme values because a lot of, for most massive production, if we naturally collect the data, the critical data will always be sparse in a very large domain. So we need to be able to extrapolate from the head to the tail. So the head model is defined as the majority part in the distribution of a certain parameter, while the tail has a more rough and sparse data. So for example, in driving, the head means you have a comfortable driving environment that people are usually not that aggressive. But sometimes you will encounter some people will have road range that will very abruptly cut in. So the challenge, the task is how we can predict the behavior of the tail, use the data in the head. So this extreme value and this data imbalance can be very extreme. For example, with some simple statistics, people estimate that you need 11 billion miles to prove an AV is safer than a human driver in a naturalistic driving. So 11 billion miles is a very large number. That equals you drive from here to the sun and come back 100 times. So we cannot really conduct such experiments for every new version of your software. Right? So we need to do some smarter things. And one way to do that is through data reweighting. So you know you need more data in the tail because the cost or the risk lie in the tail. So we can shift our sampling and make it different from the naturalistic distribution. So we can sample instead of this blue curve, we can sample at this red curve at the tail, cross the boundary, at the boundary of to be safe or unsafe. So this can be done, and then after you collect the data, you can remember how to skew the statistics from px to pure x, and you can calculate the expectation in the original space with important sampling. Right? Remember how you shift the distribution, and use that as a weight to give the weights for the collected data in the new distribution. So this is important sampling. In the classical important sampling domain, people have a concept of dominant point that can be used to guarantee the efficient convergency. So for example, the dominant point for this 1D space is this boundary between safe and unsafe. For example, in 2D space, the dominant point will also at the edge of the boundary between the safe set and unsafe set. So you can, instead of sample here as a naturalistic setting, you should sample on the boundary. In this case, we can prove we have exponential convergency of the risk we will encounter. However, for real world application with a high dimensional input, it's actually not that easy. For example, if you have two kinds of different failure mode, and you only sample one mode and shift the distribution from the normal distribution to the nominal position to only one to the mode, and you only sample there and ignore the other part, it's a huge risk. One potential case is that you ignore the other mode, so you underestimate your risk. The other one, if you're in a rare case, that you happen to sample the other case, but because you already sampled it here, then this kind of phenomenon will result in instability of calculation. So you will have very large variance in this case, and make it convert even slower than a nominal sampling. So that's because the high dimensional space of the intelligent autonomy. And in high dimensional space is very common in the intelligent autonomy. That's actually how we define the intelligent autonomy, that is able to deal with high dimensional space. For example, the high dimensional may come from vision. For example, this is like a sign recognition. You have images, and input space could be millions of pixels. It could also result from the temporal space. So even you design autonomous vehicle, you have several cars in the nearby area, and you drive for a certain time in certain time interval. So you have dynamics at different time. So it's the high dimensional with vision times the high dimensional at time, in time. So high dimensional is very common. So how to do that? So one of the approach that I'm working on in the past years is that we say to beat a beast, you need another beast, right? So to deal with high-dimensional space that's created by deep learning, we also use the deep learning to help the importance sampling. So this is what we call the deep importance sampling. The idea is very straightforward. That is, if you want to estimate the dominant point of these risky areas, you use deep learning to estimate the boundary. So that after you estimate the boundary, let's assume that deep learning uses activation as a ReLU, which is a linear piecewise function. Then you can move the distribution to each of these edge in the piecewise linear function so that the whole problem converted to a mixed integer programming. And mixed integer programming has very standard solutions and packages. So you can discover those important areas. This is a good problem. This is a good method. However, doing so, that is, you need to consider every edge of the deep learning, right? But you may have like millions of neurons, and you need to consider millions of Gaussian distribution. That can be very, very computational inefficient. So next step to solve the computational problem. So we already solved the sampling problem with the deep importance sampling, but how to solve the computational problem? We propose the computational efficient and robust evaluation of safety package. In this case, so we are using this is original deep learning that have many edges. It's the same number of neurons we use. The number of edges equals to the number of neurons we use. We can simplify that by linearize part of the deep neural network so that we are trump those unnecessary neural network, and we have some the outer approximation with the neural network so we can still have a similar performance. The improvement is great, is significant. So if you only use naturalistic way, for example, in this kind of simulation of this 3-car simulation, you may need to run a month. The computation need to run a month. So it's very heavy even for simulation and expensive for simulation. Well, with deep importance sampling, so we reduce the sampling to very small number, but we have relatively larger computational time in this light shading area. Furthermore, we chop the neural network to a degree and created this certified approach that we almost have the same sampling data efficiency, but here we also have the computational efficiency. So that only takes 2 hours. So this 2 hours of performance is equivalent to a month simulation. So think about if you launch a company, right? So you spend, these days, a lot of companies, they just run GPUs. That's maybe the most costly asset you have. If you can save 20 times 20 cost by these 2 steps, so how much money you can cut in this case, and also time. So I think this is important. So I ramp up this research into a certain flow. So first you collect data in the real world. Then you build a simulator for the real world using naturalistic statistics. You skew the statistics and create an accelerated environment. And then you can, from this environment, you have 2 things. One is you can estimate the risk. Another one, you can identify the important failure examples. Then you can use the importance sampling skill to convert the result from this accelerated environment to the naturalistic environment and understand the risk of large deployment in the original space. So to achieve these 4 steps, you need 3 skills. One is you need to have a good generative AI that can simulate the world. Second, you need you have a toolbox of importance samplings such that you can deal with the high dimensional in input space and also in time space. And finally, you need to some way to really implement the sampling in physical world or in augmented reality. So after that, you'll be able to access the safety, the level of risk, and then you can make decisions. So to make decisions with the safety, so we augment the traditional Markovian decision process that try to optimize the reward with another cost. So you are not only maximize the reward function, but also you have a constraint. If you're smaller than kappa, then your safety level is acceptable. So that will be the constraint optimization problem. So this kind of constraint optimization problem is naturally a multitask problem. So you have potential two risks by imposing this constraint. One is your training can be unstable because you have constraint, you have optimization, right? So these two will intervene with here. You have training instability. You also have some issue for deployment. Well, this optimization may not be robust to the uncertainty. So why? Because think about this. So this is the two areas that I showed in this constraint optimization. You want to optimize along the x-axis for your reward. You also want to keep the risk under a certain threshold. So the feasible set for our policy here, each point is one policy. The feasible policy will be below this threshold. So the shaded area is all the feasible policy. And if you want to do optimization, you want to increase the x value and also make this y-axis value smaller than the threshold, then naturally the optimal policy will be here. So what's the problem with that? The problem is that you're on the boundary of safety. No matter how designed it, you'll be always on the boundary of safety. So you always have a temptation to go to this area because you want to increase your reward. So whenever you do increase your reward, you'll cross this boundary. So if even you can search for the optimal solution, then if there's any disturbance in the system, you will cross the boundary and become unsafe. So that's what we call temptation. So this phenomenon is very easy to understand, but very lightly studied in the reinforcement learning domain. And you may argue, okay, what if there is no trade-off between the safety and the performance? In this case, you have this kind of negative gradient between the safety and the reward. In this case, we call it trivial safe reinforcement problem because you can just ignore the safety. You naturally will result in a safe zone. So but however, in the reality, almost all the problem I encounter has this trade-off between the performance and your safety. So how to deal with that? So you can see here, the safe RL is not robust. There's a simple example I showed. So for example, this car just want to move along the periphery of the circle, but need to avoid this yellow area. So the optimal solution will be you just follow this going straight at this area and then follow the circle otherwise. So if you give this the perception system a little bit disturbance and noise, then the training will be very unstable and the deployment can be very wrong. So that's what happens on the right. So because this intervene between reward and the safety constraint, the traditional robust reinforcement learning will not work. So robust reinforcement learning means, so I will give you the worst, and hopefully you can handle the normal, right? So in this case, for example, one SOTA algorithm called MAD, they want to perturb your action as much as possible, will not work in this case. Because in this case, you are nudging, it's like you are driving, but there's another person always nudging you. You can very hard to learn what is safety because you will always get this distraction, right? So we want to, then what to do? So we want to say you can either, like precisely whenever there is a safety issue, you'll nudge that person, but keep it quiet when it's normal driving. So then that person learn, okay, I can now drive too fast. But interestingly, this is normal. This is the first approach. Maximize the worker will maximize the safety cost, so that you are resilient to the infeasibility. The second approach, which is I think very interesting, of this two-dimensional optimization, is that instead of perturbing this in the y direction, you can also perturb it in the x direction. It's like you're encouraging the driver to drive faster. You say you're super good, drive faster, you can do more. And then eventually this driver will have the issue, right? So safety issue. So this is another way. You can also perturb in the x direction. And the interesting thing we found, if you can actually make this two adversarial, you can use these two adversarial together and have a very versatile and robust perturbation to the system, and let the system learn how to keep a distance from this threshold. Again, remember, each point here represents a policy that has millions of neural net parameters. So keep a distance from a certain line is not that trivial. Okay, so then after that we say, oh, we can also improve the efficiency of the system. We make the system even harder. So here we are using the system called safety gym. So this agent want to go to the each dot, will avoid this blue static up circle and this moving purple up circles. So we compare our approach with other approaches. So you can see all the old policy approaches that use historical data will fail to satisfy the safety constraint. It should be below this red line. But all the on-policy approach are capable to keep it safe. However, if you look at this figure on the right, that x-axis is how many mistakes you make. Y-axis is how fast you learn. So you can see our method can be zero magnitude of efficiency than them because x-axis is actually in the log scale. So using a constrained variational policy optimization, so we can actually make our robot learn much faster with the same number of mistakes. So this is really important as well. So not only this small robot, we also try different kinds of robots, for example, spider and drones. Drone is actually very, very challenging because if you have a certain safety problem, drone will fall to the ground and you basically cannot learn too much from it. So it's very sparse reward and cost trade-off. So not only safety, this method actually, when I call it safety, I actually means any critical metrics that you need a threshold to make it acceptable for other people in the society. For example, it could be a bias and fairness. It could be some energy consumption for sustainability. It also could be privacy leakage. So they all have similar issues. Once we have a large-scale deployment, those harmfulness will actually show up very, very significantly. So that's the first challenge. The second challenge is that not only you need to extrapolate to the tail, you also need to deal with new tasks. The new task is the problem comes from that you can, sometimes it's a multi-modal, you have a different mode, and it's very challenging to model them with a single neural network. You'll overfit. So you'd better have a conditional distribution. That conditional what task you are, you will build the distribution. So this is important. For example, you need to learn how many tasks you have. For example, this kind of a task. So if you design a car that drives in this kind of simulation, this environment, it can be really difficult to use a single neural network model everything happening here. Right? You can say it's really very intelligent. It's driven by, it's not a movie. It's indeed happened in Ethiopia that you have many cars, many lanes driving together with the pedestrian buses and trucks. So how to deal with this situation? So the challenge is that you do not know how many vehicles will surround you at each time, and you do not know how many scenarios there are. So I told my student, okay, if you want to start it from generalizability, start from here. So if you can solve that problem, you probably can solve all the problems in driving. So we didn't go to Ethiopia. We download the video from YouTube, and we do some image processing to have the location of each car. And then we model, because the number of cars change all the time, so we use a Gaussian process to model the field, so how other vehicle will interact with you. And we use a hierarchical derivation process to sample how many scenarios you are. So basically, that's unsupervised learning. And interestingly, we found that there are 8 different kinds of scenarios. If you can handle them well, then you're almost 80% time you're fine. So it's a little bit complicated than our normal driving situation. But obviously, people over there already recognize these patterns. That's why actually they can drive, right? So they can generalize. So then we say, okay, so after you can model the situation, you can make decision. So we put this model into this reinforcement learning domain, and we make this a model-based reinforcement learning. The only difference is that this model can sample different tasks at each time. So if we observe some scenario that is familiar to what I have seen, I will take the old model, I bring out of the old model. If I have seen something really unique, I model that a new one and start to learn a new model. So that's the task agnostic and model-based reinforcement learning. Well, since now we have tasks defined in this unsupervised learning. However, when you bring in the task, it also bring in some issues. You can have redundant tasks. You may miss some tasks. You may also have wrong label tasks. This all because of the imbalanced data size between the tasks. Right? So, for example, we start to solve those problems we encounter. For example, in this case, when you do the manipulation, the different locations of the object should not be considered different tasks. It's just similar to say that for different, this is the same scenario. If you rotate it a little bit, you should still consider the same task. Purely statistical method cannot capture this. You basically need a way to really incorporate the symmetry into the analysis. So what we did is we incorporate an equivalent convolutional neural network and converted everything and trained and converted everything into this symmetric space. And then we can do the sampling and analysis and learning in this symmetric space. So that, in this case, if we change the location of the task, if we change that to the 3D dimension of the task, it can be still considered the same task. So even though certain tasks have a lot of data, we will not divide them into different tasks to have redundancy. Another example is that you may miss some tasks because that task is particularly hard to collect. For example, in self-driving case, it's very easy, relatively cheap to collect the data for normal driving. You may collect a lot of them. It's also relatively easy to recognize data that have collision because the police will come, right? So, basically you record what happened and do the reconstruction of the scene. It is very challenging to collect data for near misses. That something, you frighten another, people got frightened, but there's no collision. But that's exactly the self-driving car should pay attention to at this stage. So collect those kind of data is very challenging. So what we did is we have the data set of the normal driving, we have the data set of the collision, and we use the this conditional variational autoencoder to incorporate this tool, such that we can, by tuning the weight between these two data sets, we can generally style the scene that is more similar to safe or more similar to unsafe collision scenario. So we have a linear interpolation of the latent space, so that if you tune this lambda to 1, it'll be fully safe, it to 0 to be fully collision. In this case, we can interpolate them and generate some near misses. So near misses should be another task in this case. So that's another example. So what if the models sometimes the models are super big. For example, nowadays where transformer models are very popular. So, we say, in this case, the data may not almost always not insufficient. So instead of the index to indicate each task, we say maybe we can use more information from this data we collect for each task. So the first, because those transformer models you can see they're super big. For example, RoboCat that just published by DeepMind has 1.2 billion parameters to train. Right? How many experiments can you conduct? Right? So that can be extremely challenging. So how to build a more informative index. So what people did in natural language processing is that they are using so-called prompt-based learning. In this case, you give some guidance to the machine so that you can generalize much more with a better direction. So then what will be the proper format for prompt for autonomy? So we are using, in this case, we are using demos as a prompt to train the robot. It's like you have a robot at home. You bought a robot, right? And then you say, okay, I will show you how to clean the floor, but only twice. Okay, after that, you need to figure out yourself. You can use this tool demonstration by you as a prompt and give it to the robot. And the robot will be much more efficient and helpful to the robot in this case, given the prompt. So we just given the experiment as the demonstration as a prompt and input that into the transformer structure. We found that will be super efficient in learning tasks and handling different kinds of tasks. So you can also have a hyperparameter, a hypernet, to incorporate the same prompt and directly change certain part of the transformer to make it more expressive. For example, you can only change 0.5% of the parameter in the transformer and let the robot to be able to handle some tasks it have never seen before. So this are also shown to be super effective than the traditional approach by only handle at the input domain. But more realistically, so we are now using multiple tasks at the beginning that the robot is usually trained with a certain task in the factory mode. And then when the robot deployed to the real world environment, you always have some new things you want the robot to do. Right? An intelligent robot should be able to handle those new tasks. So this is a continual learning problem. That is, you always have something new to do, and you need to be able to not forget what you were taught in the past. So this is challenging because if you train a full model, fine-tune a full model, that will be either hard to adapt to the new task because the inefficiency to use a small new demonstration. And also it has because you fine-tune the whole model, it will have like a catastrophic forgetting issue. So one way is that you have a several copy of them, just like what we did in this chaotic driving intersection situation, but that will be very data inefficient. Another way is that you only change a part of the head, the model, but it's not very expressive. So a simple solution is that instead of changing that or make a copy, you make a few copies of the small part of this transformer, and once you label them with tasks. For different tasks, you change a part of the transformer. So we call this tail task-specific adapters for imitation learning, because this is similar to the tail of the real-world animal, that they are all light-weighted compared to the body. They will not negatively affect the body's functionality, and they can also be used differently for different purposes. So what exactly we did is we have 3 ways to impose, 3 places to impose such a small change. One is you can use in sequential way. You can put that into the transformer. Another one you can use in parallel to the weights of the transformer. And the third one, just as we discussed, you can use as a prompt. So these are the 3 ways. And we found actually they can be very effective. We tried with 130 different tasks, and in the whole household robot, and we divided into the kitchen, spatial, goal, object, living room, and study room case. And we test. This figure shows that our model can learn things much faster, as this red curve shows, but also do not forget after this task is done. Well, other models, you can see, even they also learn, they quickly forget the tasks. So compare to these 3 tasks, and we found that the parallel approach is more effective than the sequential one and also the prompt one. So essentially, we only changed 0.1% of the parameter, but we saved a big portion of the memory and the computational efficiency. and achieve the backward transfer capability, which deal with the catastrophic forgetting, and also the forward generalization capability. So, and also this task can be wrong too. So we sometimes, we divide into this task into 5 categories. But sometimes the category can be wrong. For example, if you put this, you have a studio, right? So it's a kitchen, it's a living room, or it's a study room, right? So if you live in studio. So that can be hard because one way, again, use the robust learning, you can have the worst case randomization, assume you have the worst wrong identification of the task to its policy. That can be very conservative. Basically, the robot that dare not to do anything. Another one is you can have distributional robustness, but the robot is still a little bit conservative because you basically treat the correlation between all the tasks to be independent. But in reality, some tasks are more relevant correlated to other tasks. Some tasks may seem more often together in a particular situation. So in this case, we have this hierarchical structure of the tasks. So for example, for a new robot task, that we can have we can have likelihood of which of this task belong to which this environment belong to which tasks, and for 3 different they call task suites, they have a different likelihood for certain tasks to happen. In this case, because we know some tasks are more similar to the others, then we can incorporate this prior knowledge into the hierarchical structure. This hierarchical structure is actually very common in another application. For example, sometimes in city A and city B, you may know they have different driving styles, right? Like a bigger city or smaller city, very different drive in, for example, Ann Arbor when I get my PhD and Chicago. So in Chicago, you don't expect people to really yield to you, right? So you need to really learn how to change the lane. Well, in Ann Arbor, basically people stop and let you go, because there's almost no traffic. So in this case, if you have this, it's already in city A, you have a better guess of what the other people will do. So you will better guess what kind of task you will encounter. Right? So this is this is very common not only in driving, but in robotics. You have this level of abstraction or taxonomy of tasks, and also in robots. And the very fun thing we did is with this football, that if you, for example, how many players will against it, you may have a higher different likelihood, to play the football tactics. Sometimes if you won over like 5 other players, you may just shoot directly, versus just pass the weight and pass the ball. So have a hierarchical of this research hierarchy of the tasks is very important, and that actually enable us to develop the group distributional robust algorithm that we theoretically prove that is more effective and less conservative. So I want to say that generalization is very common. It's not only in Ethiopia, but actually in other countries too. So you really need to learn the knowledge and transfer the knowledge in this case. So there could be another situation that you absolutely have no knowledge at all. You don't have any data point. This is a real. I encountered this one at Pittsburgh. I thought they're shooting a movie, but actually that's a real accident. How to deal with this kind of things, right? So that without any data point, you need to really leverage on our knowledge from somewhere, right? So for example, what we did, we can leverage the knowledge from laws and standards that's already written. Right? You can model, for example, we work with Tsinghua University in China and digitalize all the traffic laws in China. And then during the Beijing Winter Olympic, they change the local law for a particular lane. In this case, you can easily change your logic with a linear temporal logic, and then adapt it to the new law without even need to retrain the model. So that's if you have some rule, you can embed the rule. If you have some common senses, you can use trees to very easily embed that one. And these trees also can be generated by a generative model, right? So for example, we want to generate the scenarios for LiDAR, right? So they have millions of design space. We always lack of data. So how to really generate the realistic scenarios So we incorporate 3 knowledge rule that car will not in the sky, right? So car will always almost in the same direction in one lane, and that make our generative space much more constrained and realistic with insufficient data. And then we use this one to rank the popular LiDAR point cloud object detection algorithm, and shows very effective using this we call scene attack, rather than only perturb a certain point with this LiDAR scenario. And also sometimes knowledge can be represented by a causal graph. For example, you see this you have a big bus here block the pedestrian, and there is a car coming in. So you need to understand that in this scene, these 3 cars are most important, and the reason you have accident because there's a big car parked there, and those other cars are not very important. So you need to really understand these 3 things are important. There are other 2 nodes are irrelevant, rather than just use correlations. Correlations can be very misleading. For example, there is, in the rush hour you usually drive slow, but that doesn't mean at 4 p.m. you always need to drive slow. So that's because you are in certain area you drive slow. That's because the traffic jam you drive slow, not because it's a 4:30 you drive slow. So this can be very misleading in many cases and very dangerous for a purely data-driven approach. So you can embed this knowledge into the reinforcement learning structure, and then learn the knowledge and the model together. So that can be much more effective. And this can be used to also solve the sim-to-real problem. For example, if you play a table hockey in real world, you can always play very well, but in reality it's not because sim-to-real problem. And you can impose this correlation between all kind of parameters and study which parameter has the most important influence of your performance, right? And then after you learn those things, your design space, your optimization space become much more sparse, so that you can do very effective optimization with small size of data. So then you can, with that, you can do something really cool. For example, play hockey. This is a really cheap table, so you can. It's very difficult because the uncertainty in the reality, and also play some tricks. People have try 1,000 times too. On YouTube and TikTok, they make some tricks. With this approach, you can do that with a robot very easily. Okay, so but sometimes when absolutely no data is available, then that's unknown problem, right? So creation, by the way, is actually an unknown problem, and animals are somehow really good at it. So, for example, those animals can use the tools in a way you may not expect. So how we can do that? So one interesting idea is that we can leverage information on the internet as a prior knowledge for creation where large language model. So in this case, we say, we want to bring the milk into this area, but we put a hammer there. And we can really leverage on the large language model so that the robot learn how to bring the milk with these tools. And also you also need to learn how to sequentially use the tools, and sometimes how to manufacture those tools to do something new. And here you can see if you may also need to learn how to go from sofa to the black cushion by using the surfing board, or pushing a blocks to go to the sofa, and even lift the cube by making a lever. So those are very creative ways to use tools, and no traditional approach can be able to do it. But we say, how about let's ask the GPT and what happened, right? And then we designed such a approach by using the analyzer, calculator, planner, and coder. So not only the planning and the idea is generated by GPT, but also the code is generated by it. And it seems that it works in this situation. So in this case, if you have absolutely no knowledge, you can ask all the information. You can search all the information online. Okay, so in summary, we have these 3 approaches and 3 problems when we deploy intelligent robots at large scale. And also, now we are moving to the physical world. I think it's very important to consider that the physical world, the difference between physical world and the simulation, For example, you can see, all the some vehicles, they have very different roof, right? So they have different configurations of sensors. And we realized that in one of the paper, if you change those sensor angle a little bit, the performance will drop by 10%. Well, in the SOTA baseline, data, a leaderboard, their difference only 0.1%. So it's very important to say that physical world is very powerful to solve some problem, but also could be very influential, not only in perception, but in the morphology design. So by using those tools, and we summarize all the methodologies, we can do the design and the evaluation, and towards the trustworthy autonomy. And I'm now working on some of my research become the standard and protocols. I'm also working with a lot of industry people to make it happen. So also for some academic tools, I collect data in Pittsburgh and make large-scale simulators based on some open source software. So, and also some safe RL offline tools for faster learning, for a good database, and also for offline learning. So in summary, today we talk about the generalizability, safety, evaluation, explainability with causality, a certain robustness, and embodiment. And eventually we hope we can have a human centricity approach to design the trustworthy AI. So this knowledge was summarized in my course at CMU. So we are also broadcasting the same course to Rwanda right now. So finally, I hope we can deploy the intelligent autonomy at a large scale. This is made by Confucius. I say, okay, so after you got intelligence, you really need to be trustworthy. That was basically 2,000 years ago. Okay, with that, thank you for your listening, and I welcome questions. Thank you.
Curious about, you mentioned large language models as a semantic overlay. What's your experience? Is that a promising path? Some people are, I think...
Two things I think are important, useful for large model. One is, I think it's really important to learn, to get information from normal people. And they are not structured, right? So you need to, traditionally with questionnaire, but with the large model, we can very easily to get feedback from human. For example, like a driver, he said, oh, I don't like the system. It should be driven more aggressively, right? So, or drive too slow. So you have some description in natural language. So to have the feedback and preference from human is important. Second, for certain area that you have zero data, it's also a good idea to use language to search about potential solutions. So I always think that for problem we have known solutions. We should directly use the solution. For a problem we do not know even how to start, we can use other approach to explore.
And here, and I also know sometimes people like to chat more outside rather than
I'll be
questions in front of the whole group. But thanks so much. Let's hear it again for our speaker.